start a new chapter on many particle quantum mechanics. And okay, that being said, so as I said, I will announce one day before. So next class there will be a quiz. So that's also, let me tell you. So it will be something short, not
Next means tomorrow.
Yeah.
Okay.
So
can you please do that on the next day, because I have right after the class a quiz.
that's okay. This, you don't have to prepare for this. It's not a big thing.
Oh,
It's a 5-minute thing or 10-minute thing maximum.
okay.
In class, I am not taking any. It's not a 1 hour thing whole class, right? These quizzes are different. This quiz, once you see it, you will know it. It's not something that you have to prepare hard and sit separate like exam. It's not like that. This is also true for the end-sem, by the way. You don't take it like the old school exam, like the one I gave when I was a student, like 6 hour, 4 hour exam, a mega event at the end of the thing. You know, it's a ongoing thing, and you cannot possibly learn the stuff which you have not learned throughout one semester. You cannot suddenly pick it up on that day. So just and I will also, okay, let me also narrow down the quiz. It will be on the chapter of discrete symmetries. I will also do that much.
Okay.
Okay. So we are going to start now a new chapter on many particle quantum mechanics. This will go on for next few days. And we already got a bit of flavor of this subject because we did entanglement, which was at least two particle picture. So, and we also did a related problem. There is some structural similarity between this problem and like two particle in 1D and a 2D quantum mechanics. So let's start with that. Two particles in 1D. So notice that there is a mathematical similarity in the equation, but there is a lot of dissimilarity also. Two D one particle and two particle in 1D. One major example is here you can have entanglement, and there is no entanglement in this picture. Okay, so let's say I have a wave function. I call it x1, x2, t. We have discussed this problem already, that there is some aspect of correlation into there also, that if you are measuring x, if it is 2D one particle, which means x and y coordinate, and you measure the x first, x position, and then you do the y, then the distribution changes versus when you don't measure. But let's see what happens. There is two particles in 1D, which means there are two coordinates, x1 and x2. So the Schrodinger equation is of this form, where H is, so now notice the similarity. It is very similar to this 2D equation, but it has this characteristic difference. And you know that these quantities, that I, x1, x2, t, so this quantity, dx1, dx2, it refers that the probability to find particle 1 in between x1 to x1 plus dx1 and joint probability in x2 to x2 plus dx2. So this is what it means. And you also have seen that, so let's say if I in this case also there is the similarity. So let's say I say that the probability that x1 is found at A, then you have this from A to square dx2. And you have already seen also examples of, so I'm just building up the subject from the kind of thing which is easy to connect with what you have already learned. So you have already seen an example of this kind of problem, but you have treated the problem in a way that many particle picture didn't arise. So one example you did in last semester is central force. So central force is a two-body problem, at least two-body problem. And you have learned that the way to deal with this is following. So you go to this, instead of dealing with these two particles separately, you go to a center of mass frame. the Vx1 x2 is replaced by a Vr. Is replaced by a Vr, where R is x1 minus x2, and there is another coordinate which is the center of mass coordinate, which is m1 r1. The two particles involved as m1 and m2 mass is m2 r2, m1 plus m2. So now we have discussed that if you go to this central force problem, this Coulomb potential type of problem, you can rewrite the Schrodinger equation in this frame of this capital R coordinate, which is the center of mass coordinate, where r square psi minus h cut square by 2 mu, where mu is the effective mass, mu is m1 m2, m1 plus m2. This is also you have learned probably in classical mechanics, psi plus er psi equal to E psi. Now then we said that since in the case of hydrogen atom, since the nucleus is too heavy, then we said, okay, this term is negligible, or almost it is like the picture is like that this term doesn't contribute at all to the dynamics, and then you only deal with an equation like this. So that's how your two body problem become a effective one body problem. So you get an effective one body problem. But there are cases where you cannot do it. For example, so this was the hydrogen atom, and it has the two particles involved in this was electron and proton, which are distinguishable. So now if it is a problem of two electrons, okay, then you cannot do this kind of thing, because then both of them are important. Then you have to deal with both the coordinates and this potential, which is not separable either. You cannot split it in a part of x and y. So that is where a proper two-body problem will appear. And there are examples like a multi-electron atom or like let's say helium atom or something. So this is the kind of problem we'll deal with in this chapter. So now let's take this problem. I have two electrons. I call it electron 1 and electron 2. So I can write this as a wave function, psi a in x1 and psi b in x2. So this implies that the particle at x1 in state A and particle at x2 in state B. Now you can imagine this problem as anything. You can think it as a particle in a box problem. So that means these are the single particle wave function, and that is how you can write down the generic wave function of two particle system. But that is not, so that is what we are trying to come into the point, that this is not so generic. There is an additional factor you have to include. So the additional factor is the notion of indistinguishability. So since we are now dealing with two electrons, which are identical particles, and there is nothing you can do to distinguish them. So is anybody among you is familiar with the notion of indistinguishability, identical? I mean, have you seen it anywhere in your coursework? I mean, I know PhDs and IPhDs probably have seen it, but other than that.
So this means that the idea of indistinguishability means that you cannot measure, like if you have two particles which have same suppose same mass, same charge, same spin, we cannot make a measurement and claim that the whatever the observable we are getting corresponds to particle 1 or 2,
Correct.
particle 1 or particle 2. That is the idea of distinguishability.
Very good. Now, can you tell me what is the difference between indistinguishable and identical? Are they same thing, matter of semantics, or they are used in different contexts?
Sir, they are different, sir. They are not
Okay,
the same.
how are they different?
Identical means particle 1 and particle 2 look similar, but they are not the same. They just look similar. They are identical. That means they are identical. Properties wise, they may not be they may not have the same properties, but indistinguishable means they look the same, and also they share a certain set of properties which are same. Then it becomes indistinguishable particle.
So is everybody fine with this definition, or you want to argue about it? Somebody want to argue about this?
I didn't get the identical part. Like, does he mean only the structure part or what?
Okay, continue debating on this. So I will come to this point. So these two means, so what Saifullah is saying is almost in the correct direction. So I will come to this point in another moment. So they mean two different things. So the point of indistinguishability involves an action. Okay? Action means you try to measure something. Okay? So I will explain it. Just hold a little bit. So right now, let's go with the indistinguishability, which what Safi said. It means that you cannot do a measurement which separates them. Okay? So let's say I have two electrons, like He atom. Okay? So electron 1 and electron 2, and there are two possibilities. So here I wrote down one of that possibility, that one is in state A, B is in state 2. So psi A x1, psi B x2 bar, psi B x1, psi A x1. Okay? It can be both of these two. And the point of indistinguishability, there is nothing you can do to separate them. So then I would say then the wave function should be some combination. Okay, so it could be anything. So it could be some C1 plus C2. X2 bar X2 bar. Now, as we have discussed earlier, that I can, the C1 C2 is arbitrary, and it doesn't matter if you have a global factor. So the most general way you can write it as sum A. So let's absorb this into some normalization. So psi A x1, psi B x2 plus some phase factor psi B x1 bar psi A x2. So it's the most general thing you can write. Now this alpha can be anything, and we will argue later that this alpha is either 0 or pi in 3D. So 0 means it is 0 or any multiple of 0, like 2 pi, any multiple of 0 mod 2 pi, and of course this is also mod 2 pi. So this implies the wave function, there is a minus sign. No, this is a plus sign, and you will argue that this is boson, and this is a minus sign. These things are for fermions. Now notice, there is nothing that tells you this will be only, what tells you this is only two value. It can be a third value also, some other angle. So we will argue that these things are called any angles or any on. Okay? So this is only possible in 2D. It's not possible in 3D. So I will argue that. Okay. But now you might wonder that why did I say in this way? We don't say it like that in classical mechanics, right? There must be a difference between this. In classical mechanics, we say that, let's say I have two identical particles. We say it's probability half that this happened, whether this happened or that happened. So why I am writing it as a superposition? Why I am not saying it's a 50% probability? If you measure this, you get this, and 50% probability you measure that. Somebody want to try to answer that?
Sir, the very act of measurement collapses the wave function into a single state.
But in this picture, that is the case. But when you, so what is the problem here? The problem is Let's say you have two balls, two ping pong balls, okay, two table tennis balls, and you cannot separate them. They have no logo, nothing, just a yellow ball. Okay? And since you cannot separate them, then you can say, okay, which one is which, I don't know. So let's say I pick one, and then it's 50% probability it is this ball or that. So let's say you put them in left pocket and one in your right pocket. So then you can say that since I cannot pick which one went to left and which one went to right, there is probability half of that this first ball went to the left and second ball went to right. So you can say your state is L, R, or RL. They are 50-50 probability. Okay. But here you are not saying that. Here you are saying it is LR plus RL. So this means that, right? This means that with some factor. So let's ignore the factor for the time. So why am I saying this and not that?
So
To make it
50-50%.
to make it consistent with the basis which we obtain.
Okay. Somebody else want to try it?
So 50-50% would be like we are treating the two wave functions independently of each other, and like in the adding case, it will be like we're also allowing superposition of the two wave functions.
Yes, that is what it means. But why are you doing that? So let me
The
give you a hint. You have to bring in symmetry. This is a symmetry question. It's a question of symmetry, permutation symmetry.
Bosons, for the bosons, it will be symmetric wave function, and for
Yes,
fermions, it
I
will be
know
an
that,
antisymmetric.
that is also a matter of what is what. But why is it so?
We
For
don't
Pauli
know.
exclusion principle, if
Yeah,
we
that is
put
the consequence of this. That's the consequence
We
of
don't
this.
know
But you are
which.
getting that point correctly. Yeah. So
Sir,
Modip?
We
sir, when
don't
we
know.
actually
Yeah, let
exchange
somebody
the
speak. Yeah, yeah.
sir,
Uh,
like for this two particle case, we have certain set of basis states, and even after the exchange, the overall small what to say, the probability density shouldn't change, and that's why we get these two as the cases.
No, but how is it changing in the other case? Like, why are you not thinking it as so? You are also in the correct direction, but you have to refine it a bit. Okay, Shomadip, we wanted to say something.
we don't know which state is what means.
That is correct, but
Which
that is also the premises of probability, right? The premises of probability, you don't know which is what, so you do that. But quantum superposition, why do you want to treat it as a quantum superposition?
because this is though means when we place those indistinguishable balls in two boxes, one is right, one is left. When we exchange them, we get that RL and LR. But in when we superpose them, means it's these two combination makes a state. Means
Yeah, you are
they are not.
describing what it is, but you are not saying why you need that. Okay, let me try to answer it. I would have liked this to go on, but since we have lost some time today, let's make it up. So Shafi was pretty close, and Nilanjan also hit one right point. So the point is, so this is a question of symmetry. So the system is symmetric with respect to exchange of two particles. So you can ask this. So if, so let's say there is a permutation operator which takes this x1, x2 and does x2, x1, any function. So then you expect if you do it twice, you get 1 because x1 goes to x2 and x2 comes back. And if it is so, then it has two eigenvalues. Note this can also have the eigenvalue e to the power of alpha, which I'm conveniently ignoring for now. So let's say it's also e to the power alpha. So now if your system has this symmetry, permutation symmetry, and this is in general true for anything of this sort, x1, x2, you can think this left box, right box problem also as like that. So then you want to have a wave function. Solution of Schrodinger equation is either symmetric or integer, which means it has to have this property under permutation is plus psi x2 x1 or x1 x2, or which is this is basically psi x2 x1 minus psi. Now notice that can only happen if you write it in this way. Right? This other one doesn't have the either this or this way. So this is why you are trying to find a joint eigenfunction or a joint eigenfunction of a symmetry operation. So this is a symmetry operation that you flip this thing and nothing changes. That's the notion of indistinguishability. And you are trying to find a joint eigenfunction of that. Or even if you think the Hamiltonian, if you think without the Hamiltonian, you at least want it to be a eigenfunction of the symmetry operator, which is P. And that will happen only if you write it in this way. So that is one argument. That is the main argument. That why even pure theoretically you can think you are not treating it like a classical uncertainty or classical ignorance, but rather a quantum superposition. The other way is a phenomenological thing, which one of you tried to say, that in this way you will when you allow this, you will lead to certain things like typical bosonic property, typical fermionic property, Pauli exclusion, etc. That is also a smoking gun proof that this is the right way of doing it. Okay, so now let's move on. I hope everybody is in the same page. Now notice there is a peculiarity I left as uncertain, is this notion of e to the power I alpha. So let's explain that a bit. So there is this e to the power I alpha. I said it is either 0 or pi. But why it cannot be something else? Any alpha. So to think that, let's consider the following. Let's consider the following exchange property. So notice one more thing. So this course, you will stick to this. But there is a very interesting and whole world out there on this, what happens when this arbitrary alpha. So let's consider the possibility of exchange. So let's say I have two particles in 2D. These two particles, okay? And I want to draw a diagram where this axis is time, this axis is space. These are these two particles. This 2D axis is space, x and y. And the operation of exchanging these two particles will look following. So this particle here, okay. So this is one part of exchange and the other part is bringing it back. Exchanging means I want to do this flip operation, p-square operation. So then I do this and bring them back. Now notice, if you have a diagram like this kind of diagram are called braiding diagram, because it is literally like braiding your hair. Those who have long hair knows that. So now if you want to untangle it, there is no operation you can do. There is no operation you can do which makes it look like this. Which does that, because once you have if your endpoints are pinned in 2D, if you exchange them and you brought it back and then you pinned it in 2D, there is no operation you can do to open that. Okay? Those who have long hair can try with your hair, those who braid your hair. So you braid your hair and lock at the end with a clip. There is no way you can untangle it. The only way you can untangle it, if this is not a 2D, this is a 3D, which means you are allowed to move things in up and down. Okay? Then you can untangle it. So the history of the particle matters. The history in time matters, that how are they exchanged, even if this operation is supposed to come back. So these things, there is a whole subject on this. This is called braid group and braid, all braiding process and all.
So what did you say about a 3D, that in 3D we can do that?
yeah, so imagine if you braid your hair, and at the end the edge is confined in a 2D, which means you cannot move, let it leave 2D. Okay? There is no operation you can do to unbraid it, because one end is 2D, other end is 2D, right? In a confined in a particular plane. Okay? Now in order to undo it, you have to let the particle leave that plane. Okay? So that's why in 3D you cannot have this history dependence. So that makes a big difference. So if you want to think it is an alternate way, let me give you an alternate way. This is the standard textbook way of doing it, the more formal way of doing it. So let's say I have two particles and I exchange it. And then I double exchange it. I do p square. So I want this p square to be, my question is whether this p square is going to matter on the history or not. So let me write it. Let me not complicate it. So what is this process from the point of view of one particle? So let's say you and some other person are exchanging position and then exchanging it again. So what will you see from your point of view? From your point of view, you will see that the other particle made a full round around you. Agreed to that?
Yes.
Okay. Now let's say this, let's call it a, so let's say both of you are holding a rope, and I mean you have a rope on your trajectory. So this other person will have a circular rope around you because of this process. So then can you shrink that rope to 0? If you tighten that rope, can you shrink that rope to 0? The answer is you can shrink it only if you are in 3D. You cannot do it. So if the rope is lying on floor, you cannot shrink it. If you shrink it, it will be stuck at you. Right? So if it is 3D, so if you have exchange position and there is a rope like that, and you want to shrink that loop to 0, so you can do that because you can leave that plane and you can do it in the and shrink it to 0. Do you understand this point?
No, not so clear. Means
So do you understand that if there are two persons, they are exchanging position and coming back to itself, then from one person point of view, the other person is making a circle around that person.
yes, that point is.
Okay. Now, if that person is holding a rope, then there will be a circular rope. Right?
Yes.
Now, can you shrink this rope if you are strictly confined in 2D? So let's say you are doing it on a floor. Can you shrink that rope to 0, to nothing? Are you following, Shomadip?
That point.
You cannot, because there is a person in the middle, right? You cannot shrink
Okay.
that rope, right? It will be stuck there. But if you are 3D, there are ways to shrink it, right? Because you can leave that plane.
Okay.
When I say 2D, I mean everything is 2D. There is no 3D. There is no perception of even 3D.
Okay.
It's not a part of a 2D. Okay? But in 3D, you can always shrink that rope, right? So that tells you the history of exchange doesn't matter in 3D. There is always a way to assume that their history doesn't matter. But
Like
in
in
2D,
3D, I can hire my hand and let that person go away from
yes,
the
correct.
middle. Yeah.
Yeah, the
But
rope can
how is
leave
it
that plane.
connected with the history?
No, then the point is whether you exchanged or not, that doesn't have a trace. Right? That doesn't have a trace.
Again, can you elaborate that point? Means does not have a trace means.
No,
That
if
part.
you can shrink that rope without any trouble, right?
Okay.
Then the fact that these two person exchange at some point, that is irrelevant. Their history is
Okay.
irrelevant. Right? So this doesn't, so now you can see at least one point. There is a fundamental difference between exchanging particles in 2D versus 3D. So if you now come back to this picture, what I'm saying, There is no operation you can do here and here, that allows you to untangle this trajectory. You can try it with 2 threads. There is no operation that can allow that. So the history of the exchange matters.
Sir, are you writing anything?
No, I'm not writing anything. Are you following up to this? That the history matters in 2D, in 3D it doesn't matter.
Sir, if you can untangle the strings, can't we just rotate the plane itself? The view, like what does it mean physically if we rotate the plane itself?
No, this is the so think this is a world line diagram of what happened, right? World line diagram tells you what happened in this process. So so it means that you have a starting position of 2 particle, which is 1 and 2. You did something, it is 1 and 2. So what I'm trying to say that there are 2 ways you can do that. You can either just do this 1 and 2, which means do nothing, or do something that doesn't cross path, right? That doesn't cross path. Or you can do this exchange somewhere in between, where this goes to 1, this goes to 2, and then exchange again. Then it comes here. So what I'm trying to say is these 2 things are very different objects. There is no way you can do a continuous deformation and go from here to here. Do you agree to this point? If they are locked into in this plane, in these points in 2D. Do you agree to this point at least? Yes, no, maybe?
So do you mean the particle has to pass the other particle when an interchange has to happen?
No, I don't mean that. What I'm trying to say, their path has to pass, their history, their timeline. Are you following or you are confused?
So you mean for an exchange to happen, their world lines have to cross?
Yeah, this picture, the first picture. Do you agree that these 2 pictures are not continuously deformable to each other? That is the question I'm asking. Okay, try this. Okay?
Yes,
try
means we cannot deform it in one way.
Correct.
Means
You
to
cannot
get
deform
back
these 2
one
strings.
same state, we have to deform it in 2 different ways. Means we have to twist twice to get the same state back.
Okay, I don't know what you mean, but let me elaborate it
Means
once more. My starting picture is 1 and 2 here, right? My end picture is 1 and 2 here. Now these 2 are connected in this way, in picture B, or in picture A way. Now, do you agree that there is no continuous deformation you can do in between these 2 pictures that takes you from one to another? That is my point.
Deformation means if I see the word line after some time, I will not see any change in 3D, but I will see a change in 2D,
No,
like there are crossing of paths.
wait. Deformation means you do this operation in the exchange in a way such that this is same as this.
Yeah, it will look the same. Like initially it was at 1 2. After some time it will look again like 1 2. There is no change.
So correct. So you can do it in this way. For example, your job is to go from here to here. You can do it in this way, okay, or you can do it in some other way, or you can do it in this way. Right? So what I'm trying to say, do you agree to this point that all these ways where these 2 paths doesn't cross each other versus the ways where these 2 paths cross each other are fundamentally different, because one is not deformable to the other. the initial point is same, the end point is same, but how you did it, they are fundamentally different.
Yes.
So,
Correct.
could you repeat what do you mean by like continually deformable?
So continuously deformable means you do something, you do some infinitesimal operation, continuous infinitesimal operation, and that changes one to another. So for example, these actually, if you have taken a course in topology, you must be familiar with that. But even if you have not taken a course in topology, it's probably, you can, discontinuous means there is no non-trivial jump operation. Okay, like let's say you have made a this example, one simple example is this coffee cup and donut. Okay? So there is a coffee cup and donut. So you can continuously deform to each other, but you cannot continuously deform it to a sphere. Like the sphere to donut needs a poking a hole somewhere. Right? Poking a hole means a discontinuous operation. So this is similar to that. It means if you are crossing this, it means there is a knot.
Means
You cannot
there
untie.
will be no intermediate stage. Means when
Yeah, so
I go to
if you try to untangle this, okay, let's say you made this thread picture, you will be stuck here with a knot. Do you
So
agree to
that
that?
just means that if a particle passes the other particle once, then it has to pass again to get to the
Yes,
initial.
correct,
Okay.
correct. But these two are fundamentally different. Do you agree to that?
So just by the virtue of them passing each other, right?
Yes,
Yes.
yes.
Okay.
Okay, everybody in the same page?
Yes.
yes.
Sir, is passing means
Mm,
that they are exchanging their positions, so
Yes.
something happening at
So
that
this
point.
is equivalent to this picture. This is equivalent to exactly this picture. That one case you have a loop with a point in the middle that you cannot cross, or if you try to cross it, you have to do something non-trivial. Another case, if you deform the loop continuously without any barrier, without any obstruction. Okay. Are you in the same page so far?
now, will you please explain that 2D 3D part? Means
Yeah. So did you get this point in 3D that if you leave that plane, you have 3 minutes, that you can close this loop without any obstruction in the middle. If you leave this
yes.
in this picture.
In 3D we can do that. Uh,
Okay. Now play this game. Try to do it. Okay. So now leave this rule that this particle can leave, like is not confined in a plane. It can leave that plane. Now you will see that you can deform them. That is what I'm trying to say. Anhad, you were asking something?
Yeah, sir, I wanted to ask that when we are applying P, do we mean that those exchange has to go in certain path? Like if we apply P once, then both can cross, like move in a clockwise direction and pass through each other. And then we can apply P again, but it can move anti-clockwise.
Oh, so
Then
you
we
are
won't have
asking,
any trace of it, right?
right? So you are asking, is it have to be this or can it be this?
Yeah, exactly.
Right? Yes. So what I'm trying to say, in 2D, you can have both possibilities. In 3D, because this is a trivial exchange, because this is deformable, right? This is a trivial exchange. Which means you exchange two particles, you took this to this, and you came back in the same path. This is the meaning of this trivial exchange. That is same, that has no problem. But this is a non-trivial exchange. My point is, only in 2D you have a non-trivial exchange. There is no non-trivial exchange in 3D. Did you get that point? If you got that point, then I think my message
I
is.
get the non-trivial part here, but what in 3D? Can you explain that?
Yeah, in 3D the point is, if you have a loop like that, you can always lift it from this plane and deform it to shrink it to 0.
So
Right?
lifting it means moving it in, like one particle is moving ahead in time or something,
No, no,
because
no,
we
no,
have
no.
time
It's 3D.
axis.
3D means you have this no time is like that. So 3D means you have two particles, you have exchanged it, and then again exchange it, which means you again did the second round of exchange. You brought it like this and brought this like this. Now you can do it in a way that, because you can live, you are not obligated to live in a plane, right? You can do it in a 3D space. So that means this trajectory can be shrink to 0 and as if no exchange have happened. That history cannot be erased in 2D. That is my point. This picture should be much more easy actually. Do you follow this?
So how do we shrink it in even in when the motion is in a box or 3D? I don't get it.
No, you can always do this exchange in a way that doesn't involve going to the other particle space, crossing the other particle.
Like, can you explain what are we exactly shrinking here? I don't think I'm getting that one.
The history of trajectory of one particle with respect to the other.
And how is that shrinked in 3D? I'm still not getting it.
Yeah, it's synced in 3D because, as I said, this history, you can leave this thread, this trajectory, and shrink it to 0. You have no such option in 2D. Do you understand this point?
Okay, means in 2D we have not have that extra plane that
Yes.
when we are shrinking that phase trajectory, it's have no place to go. Means when we are shrinking it.
Correct.
Means okay.
Okay, now try to do it yourself. Like take 2 points, take 2 balls, okay, and do it in a table, and try to do it on this 3D space, where you'll see you can do this. Okay, so if you're, I cannot show probably the 3D. Let me go in an angle. Okay, so first of all, the 2D is clear to everyone, right? The 3D is unclear. Is that the case?
Yeah.
Okay, so now let me go in an angle and change the plane. Okay, so now let's say I did this, okay, and I did this. Okay, but there are possibilities of doing it like this and like this. Then as if nothing happened, right? Do you understand this point? Then the loop can be shrinked. Can you try to do it with your hand and see why it is different? Okay, try to do it. But okay, we'll come back to this discussion because the class time is over. But also I want to mention this whole discussion is out of syllabus because it's a whole new subject. This is called braiding and it leads to something called topological properties because it depends on whether you can continuously deform something or not. It's very important in modern topics and especially in quantum computing, etc. But this implies that in 2D, there are 3 kinds of objects. One is trivial, okay? Trivial with a phase. They are bosons and fermions. We'll see later. Bosons and fermions. Plus, there is a third possibility, which is called anyons, where the history matters. History of exchange matters. In 3D, there are only 2 options, bosons and fermions. However, there is another thing which will happen, which we'll learn next class, which will involve actually 3 particles, and that is neither boson nor fermion. And we will see in that point that if it is neither boson or fermion, there is a third possibility will come that will be called parafermion and paraboson. And none of these are part of syllabus. Our syllabus is boson and fermion. So what I'm trying to say, in 2D, there are many ways you can do this exchange. Sorry, in 3D, there are many ways to do this exchange. And this exchange doesn't necessarily mean that you can continuously deform it to an operation that means no exchange have happened. In 2D, there is no such option if you do it the exchange in that way. Not this trivial way, but this way. Now there is even one more interesting thing is 1D. And in 1D, you cannot even exchange a particle without an interaction, right? Because you cannot leave this point. So you cannot go through each other without seeing each other. So that leads to an extra complication. So statistics of identical particle in 1D, 2D, and 3D, the operation of exchange is very different and very non-trivial. But normally, since we think of 3D world, and these are very important problem nowadays in many body physics, but normally when we deal with 3D world, because we deal with 3D world, the most common thing you encounter is boson and fermion. So bosons and fermions means this exchange can be either, this exchange is trivial, and it can give you either a plus sign or minus sign, which is because of they are eigenvalues of this permutation operator. But there is no such, that is always possible in 2D, but this is also possible that it is not just that. So that is the only point I wanted to convey. So that is all I wanted to say for the class. But if you want to stay for some more time, let's discuss about this issue again. Why 1D, 2D, and 3D are different? Okay, is there any question up to this point, modulo this confusion of 3D?
By 3D, you mean 3 space dimensions, right? So the
Yes,
world line will
right.
be like a
So if you want to
4-dimensional
draw
space.
a world line, you should draw it like this. In 2D, you are drawing it like this, right? In 3D, you should, if you want to draw it, it should be like this. It's a bit tricky to draw in 3D. That's why I was not drawing. So you can take this point, and any such operation is possible. Yeah? But this point is also arbitrarily. This is not a one. This exchange point is also 3D. So that is very important. Everything is 3D. So now that you have exchanged, and this is anywhere, right? So then you have cross exchange. So okay, let me draw this, do it by hand again. If I have anything, yeah. These are clearly distinguishable objects. So in 2D, if I do this and do this, then this loop is encircling this, right? If you want to shrink it, it will hit this object. In 3D, right? So now you can shrink it without any problem. Can you see that now? What I'm saying?
Here, shrink means you are like pulling two objects closer without crossing your hand side, just straight
Yes,
line.
yes.
Yeah.
I can do this whole operation as if I never crossed.
Mm-hmm.
I can do it like this. Like I can do and do.
Yes, yes. Mhm.
Okay. So this fundamental difference between 2D and 3D and 1D is a whole, it can be a whole course. But we will stick to 1D, 3D and stick to both. We can stick to 2D also, but we'll assume as if this third thing is not happening. But if one of you want to pick it as a term paper topic, most welcome. This thing anion and parastatistics. These are the subjects. So I will discuss about parastatistics in the next class. And this is not a part of the syllabus, but it's useful to know that there is a whole world on this. Okay, that is all for today.
Sir,
Yes.
where are these 1D and 2D cases useful, like for practical purposes?
Oh, it is normally in when you do this. So yeah, so you are asking that why do I care about a strictly 2D system? because in real world nothing is strictly 2D, right? But that is
Yeah,
not
exactly.
true. You can always engineer a system which is strictly 2D. Okay? So for example, usually these are in condensed matter, these are engineered systems are there. Normally when we think of in fundamental particles, again I have a general objection with the word fundamental or elementary, but let's use them since they are used in commonly, because who decides what is fundamental? That is my question. So why I have a general objection? Because just because you understand the behavior of a particle of a one of the fundamental particle, let's say electron or quark, that doesn't mean you can explain what happens when many of them come together, right? So then this is not fundamental. There is something else happening at a different scale, right? So that's why my general philosophical objection to that, but modulo that. So when we talk about electrons, quarks, they are leptons or gauge bosons like WZ bosons or these gluons or etc. Or photon. Photon is something you have seen. Then they are only bosons or fermions, right? Bosons or fermions. Even the composite objects like mesons or hadrons, they are bosons or fermions. But there is no analogy so because you are thinking of your these quote unquote fundamental or elementary particles in 3D, but there are objects which are strictly 2D. So one such example is, let's say you made a interface. So these are called interface device. Oops. So you take two material and sandwich them, like make a junction, a layer. Okay? And your particle, for some reason, is strictly confined to that layer. Okay? Because there is some reason that it cannot leave this because of some mobility reason that you can understand there is some constraint that why the particle must live in the layer. This is called surface. So you can engineer a system. So this was one famous example I think is, what is gallium, aluminum something. So you look at this experiment of quantum Hall effect. So it's a Nobel Prize winning experiment, which is one of the first experiments to make a strictly 2D system where the particle cannot leave 2D. Klitzing was the person.
So in this, the surface layer should be like roughly about the thickness of the
Single atom.
particle itself. Yeah.
Single atom thickness, and it
Okay.
cannot leave that plane. There is some
Okay.
physical constant. Similarly, you can have a strictly 1D system, a nanowire or something. The particle is strictly 1D. It's not a fat wire is not 1D, of course. It's one atom 1D. So these kind of examples, and then you get anions there. Then how dare you call it not fundamental? It exists in nature. You cannot break it down to something more something more deeper. Well, you can actually. There are excitations of some complex ground state which we can discuss later. So these things are possible in 1D and 2D. You can get anions, bosons, and anions. So there is one problem which I have been working on recently. It's one example. It's very different from that, which tells you that fundamentally you cannot have a motion in any higher plane. So one such example is following. So let's say, so this is something from my research, which I'm doing very recently. It's not that only I did it, many other people did something similar and they know example of this sort. But what we have is, we have an unpublished work right now working, which is something more interesting. So let's say I have an antiferromagnet. The spins are up, down. Antiferromagnet means the neighboring spins must be up and down. Now, if I delete a spin, okay, now notice this spin is locked in its space. Okay, it cannot go anywhere. because if it moves one space, this up will come here. Now this is an energetically costly thing because both a pair of spin is pointing up, which you don't want. Why you don't want? You can construct a model and show that this thing is very energetically expensive. The only energetically favorable thing is up, down, up, down, up, down. So this process is forbidden. But you can show that if you put two particles, so let me draw it here. Let me put two particles. So now it can move. Okay, it can move, like it can go here. So then an up spin comes here, and this spin goes here. Then this spin can hop there, and then this up spin comes here. Okay. So now this pair hopped one side, one direction, without disturbing any configuration. Now you can go a little difficult. So now you can see it is unable to move if it is alone. It can move when it is in pair. This kind of objects are called fractons.
So, but even the transition of that pair will cost some amount of energy, right? Like some, at least some threshold energy which allow them to
What
move.
I'm trying to say, that this process is zero cost process. Right?
Yeah, the final and initial energy might be the same, but they might need energy to transition.
Yeah. So you will understand these things. So their intermediate state, you can have some, yes, but it is not forbidden. What I'm trying to say, with zero cost, you can move this particle.
Okay.
But otherwise, you need some cost. So now let's put this thing in 2D. Now let's play the same game. Okay. Now let's say if this guy wants to hop here, it disturbs many bonds, right? It makes 3 bonds unhappy with alignment. So now let me put 2 of them. Now this guy moves here, this up comes here. Now this guy moves here, this up comes here. So nobody is unhappy. Okay.
Which one exactly moved? I couldn't follow.
Yeah, this pair, this is the
Can you
initial
highlight-
position, right?
Can you
Now this-
highlight the pair? I cannot see that.
This can move here, and this can move here, and this guy will come here.
Okay.
Right? This is a free motion.
Okay.
This is an example where there is no problem of moving in one, where it can move only as a pair, but not as an isolated object. Now let me give another example. Okay, now let me give another example where that is. Now I'm going to give you an example where it cannot move in. Now it can move in both direction, right? This pair can move in this direction. This pair can move in this direction also. But let me give an example where that will not happen. So now let's see. I put it in a honeycomb. Okay, this is unpublished result from my work. But it is not that this is the first example. It's possible people expected that can happen, but how to do it, that is a little tricky. So let's apply the rule that you have an antiferromagnetic chain coupled ferromagnetically, okay? Which means up, down, up, down, up, down. But this must be coupled ferromagnetic, which means up, down, 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 up. Now this coupled ferromagnetic, which means this direction you have FM, this direction you have AFM. Down, up, down, up, down, up, down, up, down, up, down, up, down, up. Okay, now let's play this game. Let's put one hole first. Now the hole moves here. This comes here. It makes everyone unhappy, right? At least two bonds unhappy. Now let's make two holes. Okay. Now this guy moves here, the up comes here. Now this guy moves here, the up comes here. Okay. Now everybody is happy, no problem. It can move in this direction. But let's try to, so now this hole can move along this line with no problem, just like this process. You can play this game. I'm making everything classical so far, but you can actually do a second order perturbation theory to show all this in a quantum context. But I'm just giving you an idea that how this move hole, so everybody is in the same page, whoever is there, that the hole can move in this direction with no problem, just like in other example, right? Now let's say the hole tries to move in this direction. Then there will be a trouble. The hole tries to move in, let me change the color, in this direction. Why? Because the up will come here, the down will come here. Okay. Now this comes here, so the down comes here. So the final configuration is this hole is here and this hole is here. But now you have a down here, which you don't want. So the hole cannot move in this direction, but it can only move in this direction. And thirdly, you cannot even take them apart. Away from, so this example, you could have taken them apart. Like it could have come here, it will be down, and then there is no problem. It can keep going. Right? In this problem, you cannot take them apart. It can move in both directions. In this problem, you neither can take them apart nor it can go in any other direction. It can only move in one direction. So effectively, you have a 1D problem. You can do further. You can confine it in a 2D plane in a 3D and cannot take them apart. So this is also an example of something analogy of quarks, because quarks, you cannot take quarks apart in a meson. This is an analogy of analogous to mesons. It's an example of asymptotic freedom. But the main point I'm trying to make is not that. Main point I tried to make is that this particle is strictly confined at a dimension lower than where it is supposed to be. So this is an operational prescription how to do that. Okay? If you have a model like that, and it turns out there exist systems which are like that. Everybody is in the same page?
So
Yes,
it
sir.
can move the same way down, right? Like we could have like on the third position, it could come back. Like the same way it moves to the right, like in your hexagonal diagram, we could have it move down, right?
No, it cannot. That is what I'm trying to say. Because, okay, let's clean the picture and show you why. Okay. So let's say this goes here. Oops. Okay. So this comes here. So now this down goes here and there is a hole here. Right? Now this comes here.
So the down can go like 2 spaces away into the first.
Now
Yes,
the
sir.
hole is here, right?
Yes, sir,
This is what is the meaning of down movement, right? The hole are in
Yes,
these
sir.
two empty spaces.
Yes, sir.
But this is a costly configuration, right? because of this bond and this bond, right? Do you follow? So
So why is
right-wise
that
movement,
costly configuration for that vertical line? Those
yeah,
are in
because the
up-down
vertical
state.
line is supposed to be same spin. What did I
Okay,
say?
okay.
Is that this line happens
Okay,
the
there is
same
ferromagnetic there.
spin.
Okay.
And the way to construct this model is say this is positive in sign, and one of them, so Jz is positive in the vertical direction, and parallel direction it is negative. So no, it is negative here and positive here. So negative means they will like to align, and positive means they will like to anti-align to reduce the energy. Right? It wants to be negative overall. So you will learn this thing later. But let's not worry about that. But let's say I just give you a rule that these guys for some reason want to be aligned, same direction. These guys for some reason want to be
Okay.
anti-aligned. If this is how I set up my system, my Hamiltonian, yeah, these kind of Hamiltonians are real world Hamiltonian. It's not. It's like it's called mixed antiferromagnetic ferromagnetic direction. You can construct this. So if I set up my problem like this, then I can show that first of all a single particle cannot move, but a pair of particle it can move, but only together and only in one direction. So this is an example of how you can confine a particle at a lower dimension, even by in principle, without doing just by the Hamiltonian. But these are very frontier problems. Okay, but this one was done long ago, 1984, even before that. These are called surface physics, which means you create a strictly 2D problem. But the system, the mobile electrons are all living on this interface. Other electrons are not mobile for some reason. Some physics is there. So this is what I wanted to show you, that there are examples where you cannot let you are forced to think in terms of a lower dimension. And then in such scenarios, you have to worry about the history of exchange. In the same page?
Yes, sir.
Okay, good. So these are very fascinating problems, and they are very fundamental problems also. One thing that fundamental only happens at deep down quark anti-quark level, but not necessarily. It can happen even with electrons in a small tabletop setup. Okay, if that's all, yeah, we can end for today.
Sir, can you just brief about parafermions again?
I will talk about it tomorrow.
Okay, sure.
It involves 3 particles.
Yeah, all right.
Yeah.
So when we say we are shrinking the particle, are we saying that now the particle is only allowed to move in 1D?
No, what do you mean by that? I didn't follow.
I mean, when we say that the particle is moving in 2D plane and it covers like it moves 180 degree, and after that when we want to shrink it,
You're
while
talking about this
shrinking,
picture, right? You're talking
yeah,
about this picture.
while
Yeah,
shrinking
I'm
we are
saying
just
it is confined on there. So let's say you are doing this exchange operation with disks on a table, and you are not allowed to let the disk leave that table.
okay.
Versus you're doing it with balls in 3D, because disk is a totally 2D animal, right?
Yeah.
So did you read this book called Flatland?
No, sir.
So look up this book. It's a funny thing that somebody imagine. It's a 18th century book on social hierarchy, or it's a satire. But they imagine that there is an animal in 2D. There is a 2D world. Flatland means 2D world. Some organism. But the problem is that organism cannot be like a human-like organism, because then the digestive tract of the animal will split the animal into 2 parts. Right? So this is a
Yeah.
fundamental problem of having an animal like that in 2D. It can be like something like amoeba, which takes the food somewhere, keeps it and rejects it somewhere else. But it cannot be
Now, what
something
was the
like,
name of the book?
huh? What?
Name of the book?
It's called Flatland. There is a movie on it in YouTube also. Somebody made a cartoon movie on it. And somebody from 3D world comes and doesn't and sees this world, and the 2D guys doesn't understand what the 3Ds are saying because they don't have any experience of that dimension. It is like earlier I told you, right? You can write down gravity in 2D or Coulomb's law in 2D. It will be very different. You'll get a logarithmic form. You won't get inverse square because of flux conservation. But it is strictly 2D, okay? Because it's not like a 2D embedded in 3D. That's what we always tend to think. There is no concept of a third dimension. If that happens, then it's very different problem.
Okay.
Sphere from 3D comes in 2D, so it were like size changing circle. What does it mean?
The flatland itself, now the sphere comes, and when it's moving down 2D, it seems like the size of the circle is changed.
Yeah. You can think it like a point and all. So yeah. So how is it's a projected object, right?
Yeah,
It's a
exactly.
projection.
Yes.
Yeah.
Mm.
Very interesting. Yeah. You can share it in. I will share it in Piazza also. What is this YouTube thing? I don't know. So
It is a
dimensionality.
video related to Flatland only that Byte added.
Okay. Okay. So the dimension is a very key player. What I'm trying to say. And this is also another campaign of why condensed matter physics is cool. You get to play with that in condensed matter. You don't get to play with that in other subjects. That manipulating dimension, it's a thing. And emergent physics because of that. Okay, cool. That's all. See you then.